Hello students, in this video we are going to discuss the basic concepts of projectile motion from the beginning, the basic theory. Let us begin. So here, let us say that there is a football on the ground. Take the x-axis as our horizontal ground and the y-axis vertically up into the sky, and this ball is kicked with the initial velocity making angle theta with the horizontal. Then this football would be following this kind of path. As you can see, it's a curved path, and later we'll see that this curved path is a parabola. In the second part of this video I will show you the derivation that this curved path on which anything moves in the air is a parabola. Such kind of motion is called projectile motion. Projectile motion happens whenever we throw any object at an angle theta which is not 90 degree, because if this angle theta is 90 degree, then the particle would go vertically up and come down vertically down along a straight line. But if the angle theta is anything other than 90 degree, then the particle would go in a parabolic curved path, and such type of motion is called projectile motion. There are so many conceptual things hidden under this topic of projectile motion that everybody should know. Let's learn one by one. So the first concept is about the instantaneous velocity vector. See, this velocity vector at this given instant when it starts the motion from ground, you can see this is the instantaneous velocity vector, is always a tangent to the path. Now these dots are representing the positions of the ball at different instants of time, and at every instant of time the velocity vector would be along the tangent to the path. This is the first important concept, that the velocity vector is always a tangent to the path on which the particle moves. We can clearly see that the direction of the velocity vector is continuously changing because it is not moving in a straight line, it's moving in a curved path. Furthermore, what about the magnitude of the velocity? The magnitude of the velocity decreases up to highest point. Although I have used the same symbol V everywhere, but please don't think that the magnitude of this velocity is same everywhere. Actually, what happens when the particle is thrown, then as it rises up, its magnitude of this velocity will decrease. Let us call it a speed. Magnitude of velocity is also called a speed. So the speed would decrease, and during the downward motion the speed will increase. However, velocity at the is minimum at the highest point, it is not zero. It must be noted that at the topmost point here velocity is not zero. When the velocity is zero, if you throw this projectile at theta 90 degree vertically up, then as the particle goes up to the maximum height here stops, here velocity becomes zero and then it begins to fall down. But if it is a projectile motion curved path, then the velocity at the topmost point is not zero. In fact, it will be a minimum value. I will show you later in the later slides why it is not equal to zero. So very important concept to note here is that firstly the velocity vector is everywhere tangential to the path, and secondly it doesn't become zero at the highest point, and as the particle rises up the speed decreases, and as it falls down for the second half of motion the speed increases. And why it happens I am going to explain next. So here, just for an illustration purpose, I have given some numerical data here just for the sake of understanding. Let us assume that the particle started with a velocity of 100 meters per second. Now as it rises up, 100 becomes 60, then 60 decreases to 40, and at topmost point 40 decreases to become 20 meters per second. Now as it begins to fall down, because of the gravity the speed begins to increase. So 20 becomes 40 meters per second, then 60 meters per second, and then 100 again. You will notice this 100 starting point, the velocity here was 100, landing point also same speed. So the particle is located at same height two times during the motion. Please observe the diagram. For example, this point and this point. you can see that during the projectile motion, of course, a particle is at the same height 2 times during its journey. For example, take this height. For the first time when it was going up, then it passes through this height, and while coming down, it again passes through the same height. And it is interesting to know that the magnitude of velocity is the same, 40 meter per second here and 40 meter per second here, both places. Similarly here also, you see, these are the two different positions, same height, but the magnitude of velocity or the speeds are equal. This is another one of important concept that one should remember, very useful for solving some problems. Now, at every instant, the instantaneous velocity vector, that means this velocity vector, can be resolved into horizontal and vertical components. Now you know that any vector can be resolved into rectangular components. You see here, everywhere the velocity vector has been resolved into two components. One is called Vx, which is along x-axis, and other is Vy along the y-axis. So every place, each velocity vector whose direction is getting changed, we are able to resolve the components along x and y directions. In fact, how to find the components of a vector is explained in another video in my playlist. You please find out this screenshot or this thumbnail, and you will find out how to find the components of a vector. So you can see that at every instant of time, we are able to find out the components, horizontal and vertical components Vx and Vy. And one interesting fact to know, that at the topmost point, you see I have not shown these two components because actually this vertical component of velocity Vy becomes 0 at the highest point. That is why it is not shown here. Further details in the next slide. Now, so here you can see it is the same picture. The velocity vectors has been resolved along the horizontal and vertical directions. Now let us talk about the force of gravity. You see this motion, the motion of a projectile is actually motion under gravity, because as the particle is moving in the air, the gravity is acting on the particle, and the force of the gravity is always acting vertically downwards. We know that the Earth's gravity always acts vertically downward. There is no other possible direction. So it can be shown using these vectors. These are the forces acting on the particle. You see everywhere, wherever the particle is going, the force of gravity mg is always acting vertically down. It never changes the direction. Gravitation does not change the direction at all. Whatever be the direction of velocity vector of the particle, you see, whatever be the direction of velocity vector, the gravitational force is always acting vertically downwards. There is no other direction for gravity. One should also notice here that at the topmost point, the angle between the gravitational force and the velocity vector is 90 degree, and before the topmost point, the angle between the velocity vector and the gravitational force is obtuse angle. Here everywhere obtuse angle, and after the highest point during the downward motion, the angle between the velocity vector and the gravitational force vector is acute angle. So it changes from obtuse to right angle and then acute angle. Now, in the absence of air resistance, yes, we will assume in the study of projectile motion in our syllabus, we completely ignore the air resistance. So we assume that only the force of gravity acts on the particle, and which is always vertically downwards. So then we can conclude from this figure that if the force acting only in the vertical direction, then along the horizontal direction the force must be 0. So before we move on to the next slide, we should remember this in our minds, that in a projectile motion the force is acting only in the vertically downward direction, and along the horizontal direction force is not acting. Let's move ahead. Yes, now according to the Newton's second law, this is the Newton's second law, acceleration A is equal to F by m, or F is equal to ma, same thing only. Acceleration vector A is equal to force vector by mass. According to the Newton's second law, the direction of the acceleration vector must be along the direction of the net force. Please see here from the formula, as acceleration vector is equal to force vector divided by mass, so this clearly indicates that the acceleration vector must be along the same direction of the force vector, and that force vector is nothing but mg is the gravitation force, divide by mass, so m cancel, mass cancel, we get g. So acceleration of the particle is nothing but the acceleration due to gravity. So therefore at every instant the acceleration acts vertically downward only. See, let us see the figure first of all. Look at this. In the previous slide I showed you that the gravitational force was acting vertically downwards, and according to the Newton's second law, the direction of acceleration must be along the direction of net force. So the net force acting on the particle is vertically downwards. It is only the gravitational force. Therefore the acceleration must also be in the vertically downward direction, which is equal to g. So now in this figure we are showing velocity and acceleration both. We can again observe that the angle between the acceleration vector and the velocity vector is 90 degree at the highest point, whereas before the highest point the angle between the velocity vector and the acceleration due to gravity is obtuse angle, and after the highest point during downward motion the angle is acute angle. So this acceleration is nothing but the acceleration due to gravity. So one must now remember that projectile motion is nothing but motion under gravity, and also you please notice that the acceleration due to gravity always acts in the vertically downward direction. Also one more point to be noted, at the topmost point only the vertical component of velocity has become 0, but the acceleration never becomes 0. Let's proceed. Now same figure only, velocity vector is shown, their components are shown, and acceleration due to gravity acting on the particle is also shown here. Since the acceleration or the force acts along the vertical direction only, we have seen in the previous two slides that the force of gravity is acting downwards, and therefore the acceleration due to gravity g is also acting downwards. Therefore only the vertical component of velocity will change. Now look at the diagram carefully, students. Here let's say at this instant this velocity vector v has been resolved into two components. One is vx along horizontal and one is vy along the vertical. Now the acceleration is acting along the vertical direction only, and we know that only acceleration can cause the change of velocity. What is the role of acceleration in kinematics? The role of acceleration in kinematics is to change the velocity. Now if you observe the diagram carefully, everywhere at every instant the acceleration is acting only along vertical. Therefore only the vertical component of velocity is going to change, and along the horizontal direction the net force is 0. Thus the horizontal acceleration is always 0. See, there is no force acting along horizontal. So according to this formula, that acceleration is force upon mass. Along x direction force is fx divided by mass, but the force along x direction is 0. 0 by m is equal to 0. Therefore acceleration along x direction is 0, or we can say horizontal acceleration is 0. So horizontal acceleration is always 0, thus horizontal component of velocity remains constant. Very important point to note here. Acceleration causes the change of velocity, but acceleration is acting only in the vertical direction. Therefore only the vertical component of velocity must change, and horizontal direction there is no acceleration. Ax is 0. Therefore the horizontal component of velocity must not change. Let us take some numerical data here. First of all, let me give some values to Vy. Suppose at the starting point the particle started the motion. At that time the initial velocity in the vertical direction was let us say 60 meter per second. As the particle rises up and up and up, look at the values of Vy. What is happening to them? It is decreasing. Why it is decreasing? 60, 40, 20, 0. Why it is decreasing? Because of the gravity is acting opposite to the direction of the y component of velocity. That is why whenever acceleration acts opposite to the velocity, it decreases the velocity. Since acceleration due to gravity is acting in the downward direction or vertically downward direction, the vertical component of velocity must change. And since the acceleration acts opposite to the direction of velocity, that velocity must decrease. Whereas look on the other side, after the topmost point, the acceleration due to gravity is acting along the same direction of the vertical component of velocity, thereby causing an increase in the value of Vy. At the topmost point, Vy is 0. As the particle fall down, Vy becomes 20, then 40, then 60. It is increasing. Why it is increasing? Because acceleration is acting along the same direction of the velocity Vy. And let us see what is happening to Vx. Let us say at the starting point, the initial velocity has horizontal component equal to 40 meter per second. Then here 40 meter per second, here also 40 meter per second, 40, 40, 40, 40. What we observe here is that everywhere the horizontal component of the velocity does not change, it remains same, it is constant. Why it remains constant? Let's read once again here. Since along horizontal the net force is 0, thus horizontal acceleration is always 0. Thus horizontal component of velocity remains constant, which is explained mathematically also here, because the acceleration along x direction is 0, therefore velocity cannot change. So the x component of velocity does not change. Again observe the diagram carefully. During the projectile motion, because acceleration is acting only in the vertical direction, therefore only the vertical component of velocity will change, but along horizontal direction we don't have any acceleration, therefore the horizontal component of velocity does not change at all. Let us look at the highest point, very special point. At the highest point, what happened here? The horizontal component remained the same, because as explained it cannot change, it remains same, but the vertical component of velocity decreased to 0. Started with 60, 40, 20, became 0. Again it increases 20, 40, 60. So this is the important feature of the projectile motion, that how the different components of velocity is getting changed due to the force of gravity acting on it. Let's proceed further. Once again the same figure. During the first half motion, that means from the ground up to the topmost point, during the first half motion, acceleration acts opposite to vertical component of velocity, thus Vy decreases. During the second half of motion, that means from topmost point to the ground point, acceleration acts along the same direction of Vy, thus Vy increases. And at the topmost point here, the vertical component of velocity becomes 0, because it is decreasing due to gravity. The vertical component of velocity decreasing, till where it will decrease? Up till it becomes 0. But the net velocity does not become 0, because the horizontal component of velocity never dies out. So because the horizontal component of velocity should always remain the same, so even at the highest point the velocity doesn't become 0. See, if you throw the particle vertically up from the ground, for that vertically up motion, as the particle reaches highest point, the velocity becomes 0 and then begin to fall down. But it is a projectile motion at an angle, so at the highest point what becomes 0? Only the vertical component of velocity becomes 0. Only Vy becomes 0, Vx does not become 0. Now also note here, the vertical component of landing velocity is same as the vertical component of initial velocity. Yes, let us compare the velocity at the starting point and at the landing point. If you observe the horizontal component of velocity, that must remain same, Vx is 40, Vx is 40. And now look at the vertical component, Vy is equal to 60, Vy is equal to 60. Direction has got reversed, inverted, but magnitude is same. In fact, you should observe here, observe the velocity components at the same height two times. Look at this position and this position, they are same height from the ground. If you look at the vertical component of velocity, 40, 40, same height, same value. Here same height, these two same height, vertical component Vy 20, Vy 20. This is also same height, vertical component 60, vertical component 60. So we learn one more concept here, that in the projectile motion, when the particle is at the same height 2 times during its motion, at those two positions the vertical component of velocity will be opposite of each other in direction but same magnitude. And regarding horizontal, we have already discussed that it will always remain same only. Okay, so that was the theory of only the theoretical part we have discussed. There is another video, next video, in which I will discuss about the mathematical part, derivations and numerical problems. So before ending this video, let us just do a quick revision of the theoretical concepts that we have learned up till now. So question 1, the velocity of the projectile is 0 at the highest point, true or false? So the answer is false. Actually the vertical component of velocity only becomes 0. The horizontal component of velocity remains non-zero. You can go back to the video once again and see how I have explained that at the highest point it is not the total velocity which becomes 0, it is only the Vy which becomes 0. Only the vertical component of velocity becomes 0, but the horizontal component of velocity still remains there. Also, you know from vector algebra that velocity at any instant of time, magnitude of velocity is root of Vx square plus Vy square. Now at the topmost point Vy becomes 0, so this part becomes 0, but Vx doesn't become 0, so therefore velocity at topmost point will be equal to Vx. So the velocity at the highest point in a projectile motion does not become 0. Question 2. Is there any point where the velocity vector is perpendicular to the acceleration vector? Let's see. Yes, at the topmost point. This is the screenshot of one of the slides before. You see at the highest point the acceleration due to gravity is acting vertically down. In fact, at every moment the acceleration due to gravity is acting vertically down only, but at the topmost point only the horizontal velocity is remaining here. So horizontal velocity and vertical acceleration, you know that angle between horizontal and vertical is 90 degree, so therefore this angle is 90 degree here. So yes, there is a point, there is only one point during this projectile motion where the velocity vector is perpendicular to the acceleration vector, which is at the highest point. Next, is it possible for a particle to move along a curved path with constant acceleration? Think again. Particle is moving with a constant acceleration. Now when we discuss about constant acceleration, that means acceleration is a vector. So definitely vector has a direction. So when we talk about constant acceleration, that means constant direction. Okay. So if the direction is constant, then is it necessary that the particle should move in a straight line? Let's see. Yes. Answer of this question is yes. Is it possible for a particle to move along a curved path with constant acceleration? Answer is yes. In a projectile motion it happens. In the projectile motion, although the velocity vector is continuously changing its direction, but the acceleration vector is always acting in the vertically downward direction because of the force of gravity that always acts vertically downwards. So we can say that yes, even with a constant acceleration, it is possible that the particle can move not only in a straight line, but it can also move in a curved path, and that is nothing but this projectile motion. And this path, the shape of this path is called parabola. Next question. Why is the horizontal component of velocity constant throughout the projectile motion? Yes, the reason is that, as we explained here, that because velocity can be changed only by the acceleration acting on it. Please note. And through the force acting on it. Basically, when the force acts on the body, it creates acceleration. And acceleration can change the velocity. So, velocity can change only if any acceleration is acting on it. Now we know that along the horizontal direction there is no force acting along the horizontal direction. So therefore acceleration along horizontal direction is 0. And because acceleration is 0 along horizontal, so the velocity which is along horizontal, that cannot change, because velocity can be changed only by acceleration. So now that was the end of this video, but there is a next video, lecture number 2. Don't forget to watch this, whose link I will give in the description. In the next video, we are going to discuss the derivation of the time of flight, the derivation of maximum height formula, derivation of the horizontal range formula, and the derivation of equation of path, and some questions. Maybe this video can extend to lecture 3 and 4. Please continue watching the video. If you have liked the video, please press the like button and subscribe my channel. More and more interesting videos will be coming up, and here is a screenshot of my channel. Please go through my channel and watch as many videos to understand physics, and please reply me in comments what all topics you want me to explain which you are not understanding by yourself, and any textbook question like H.C. Verma book or any other textbook you want me to solve question and explain, kindly message me. I will be happy to reply as soon as possible. Thank you very much for watching my video.